Replication is an essential concept in distributed systems. The core idea of replication is to repeat parts of the system to make it work better. Systems that are well designed run well with a single user, technically a single stream of manageable requests for which the system was specifically designed. The system can typically scale its service further to a couple of users. This means the system can continue to deliver good service here to respond to the two users' requests correctly and fast. The system can even scale its service to a few more users. However, as the number of users increases, the system cannot continue to scale its service. First, it slows down. This happens, for example, because the system has to compute a bit for each user, and then the sum of computing needs across all the users exceeds the available system capacity. Or because many users want to change the same data item, and thus, together, their requests can only be processed in the right order. There can be many other reasons for reaching the scalability limits of a system. You can see this happening in practice with systems like Overleaf or with online games, when the system cannot respond fast enough. Overleaf users will say the system is moving slowly, and online gamers will just shout, "Lag!" Understanding whether this happens because the system cannot scale its service, or because of some other reason, for example, the network is simply partitioned, is a complex challenge in distributed systems. As the number of users further increases, the system stops delivering service. It crashes. We need to do something to prevent these crashes. Any system we can build today that has only one location forms a single point of failure and cannot scale its service indefinitely. What to do? And there's a solution typical to distributed systems: replication. With replication, we repeat any part of the system so that it can provide a part of the service on its own, but together the system scales. Replication can apply to many aspects of a distributed system. We can repeat essential system parts with different granularity and different levels of abstraction by duplicating, triplicating, and more generally multiplying the same common data, as in the example in the top left quadrant labeled A, the physical nodes or virtual machines, bottom left quadrant B, the service, top right quadrant C, and even similar processes, bottom right quadrant D. In the top left quadrant, we replicate common data. Each replica or node can perform operations on its local data. If changes do not have to propagate between the different nodes, a model commonly known as sharding, then the system can scale its service indefinitely simply by adding more nodes and connecting new users to each of these nodes. This is a common model for scaling massively multiplayer online games today. In the bottom left quadrant, we replicate the nodes. Grids and clouds that offer access to virtualized infrastructure use this model of operation. So far, the replication we have shown is done spatially. Each replica is mounted on a new node, but other patterns exist. The pattern we use so far replicates spatially, with multiple nodes hosting the set of replicas or instances, as in the system illustrated here under label A. Replication can also occur temporally, where multiple instances coexist on the same machine or node, as illustrated under label B for a system that is not distributed. In practice, nodes with multiple and even many resources are becoming common, and machines with different properties are also commonly part of the same system. So it is also becoming common to deploy replicas or instances both spatially and temporally, filling up the differently sized nodes as illustrated under label C. Even more complex issues exist, such as where to place the nodes themselves. 10 in Amsterdam, 2 in Frankfurt, 1 in London, etc. But such facility location problems are outside the scope of this introduction.